Hey there and welcome. So you probably think trigonometry is all about right-angle triangles, right? Well, get ready, because today we're going to take everything you know about sine, cosine, and tangent and blast it out of the textbook and into a whole universe of rotation.
All right, let's just jump right in. Look, we all get something like sine of 30 degrees. It makes sense inside a nice, neat triangle. But what about sine of 150 degrees? You can't have a 150-degree angle in a right-angled triangle. It's impossible. And seriously, what on earth is a negative angle? These questions aren't trick questions. They show us where the old way of thinking hits a wall, and today we're going to smash right through it.
So how do we break through that wall? We need a completely new perspective. The first big idea, the most important shift you're going to make today is this. Stop thinking of an angle as just a static corner of a shape. Instead, see it for what it really is, a measure of movement, of rotation. Think about it like this. Picture a single ray, just a line pointing in one direction. That's our starting point, the initial side. Now, lock down one end of it and just rotate it. The place where you decide to stop, that's the terminal side. And the angle, it's just the amount of spin you put on it to get from the start to the finish. That's all it is. You know, this new way of thinking makes everything so much easier. We just have a simple rule. If you rotate the ray anti-clockwise, that's against the way a clock's hands move, we call that a positive angle. And if you rotate it clockwise, well, that's a negative angle. And just like that, the whole mystery of negative angles, poof, it's gone. It's just a direction.
Okay, so if angles are all about rotation in circles, how should we measure them? Now, we all grew up with degrees, but they're kind of random, right? I mean, why 360 degrees in a circle? It's an ancient choice. For rotation, there's a much more natural unit of measurement. It's called the radian. And trust me, it's the native language of circles.
So what in the world is a radian? Okay, picture a circle. Now, take the length of its radius, the distance from the center to the edge, and imagine you could pick that length up like a piece of string and lay it down right on the curve of the circle. The angle that piece of string makes from the center, that is exactly 1 radian. It's this perfect, beautiful connection between the radius and the edge of the circle itself.
Now, you could go and memorize a bunch of complicated formulas to switch between degrees and radians, but honestly, you don't need to. All you need to remember is this one single golden rule. Pi radians is the exact same thing as 180 degrees. This is your Rosetta Stone. If you know this one fact, you can figure out any conversion you'll ever need.
And you can see how it works right here. A full circle, 360 degrees, well, that's 2 times 180, so it's 2 pi radians. Half a circle, 180 degrees, that's our golden rule, it's pi radians. And a right angle, 90 degrees, that's just half of 180, so it's pi divided by 2. See? It all just flows from that one simple idea. You'll see these so often they'll feel totally normal.
Okay, quick recap. We've redefined angles as rotation, and we have a new way to measure them with radians. But how does this help us find sine of 150 degrees? The answer, my friends, is what I think is the single most powerful tool in all of trigonometry, the unit circle. This thing is the master key.
And here it is, the big aha moment. This is the whole secret. Imagine a circle with a radius of exactly 1. That's why we call it the unit circle. Now pick any point on the edge of that circle. The angle you rotated to get there is theta. Well, guess what? The x and y coordinates of that point are not just numbers. The x coordinate is the cosine of that angle, and the y coordinate is the sine of that angle. It's literally that simple.
Don't believe me? Let's try it out. Let's rotate 90 degrees anti-clockwise. Where do we end up on our unit circle? We're right at the very top, at the coordinate point 0, 1. So the x value, which is cosine of 90, is 0. The y value, which is sine of 90, is 1. It works. It actually works.
All right, let's keep going. Let's rotate all the way to 180 degrees. Now we're on the far left side of the circle. What are the coordinates there? They're -1, 0. So what does that mean? It means the cosine of 180 degrees is -1, and the sine is 0. Suddenly, our trig functions can be negative. The game has totally changed.
You can probably see the pattern now, right? Let's go down to 270 degrees, pointing straight down. The point on the circle is 0, -1. So the cosine of 270 is 0, and sine of 270 is -1. It's crystal clear. And what happens when we go a full 360 degrees? We spin all the way around and end up right back where we started, at the point 1, 0. Which means cos 360 is 1, and sine 360 is 0.
exactly the same as they were at 0 degrees. And this reveals the most amazing property of all. These functions repeat. They are cyclical. The journey starts all over again.
And this cycle isn't random at all. It's full of these beautiful, predictable patterns. Once you really get the unit circle, you can figure out the sign, whether it's positive or negative, of any trig function for any angle imaginable. You can decode the entire system.
You might have heard a little memory trick for this in school. All school to college, or ASTC. In the first quadrant from 0 to 90 degrees, all the functions are positive. Makes sense, x and y are both positive there. In the second quadrant, only sine is positive, because y is positive but x is negative. In the third, only tangent, and in the fourth, only cosine. It's not a rule to memorize, it comes directly from the signs of the x and y coordinates on the unit circle.
And all of this leads to the super powerful property called periodicity. The circle just goes round and round, forever. So the values for sine and cosine at, say, 370 degrees are going to be exactly the same as they are at 10 degrees. This repeating pattern, this is everything.
Okay, this is all really cool math theory, but let's be real. Why should you care? What's the point? Why does taking trigonometry from triangles to circles actually matter in the real world? Well, the answer is kind of profound.
Because sine and cosine repeat in this perfect, endless cycle. They are the perfect mathematical language for describing anything in the universe that repeats or oscillates. We're not just talking about theory here. This is the language physicists and engineers use to describe sound waves, light waves, the alternating current powering your home right now. The modern world literally runs on these waves.
When you think about it, we've just seen the power of one simple shift in perspective. Just by changing how we define an angle, from a static corner to a dynamic rotation, we unlock the mathematical language of cycles that helps describe the universe. It really makes you wonder, if math can so perfectly capture these patterns, what other hidden codes, what other secret languages of our universe are just sitting there, waiting for us to find the right perspective to decode them?